All right, everyone, thank you. Presenting a minimally invasive blood glucose monitor and insulin delivery system. So blood glucose concentration is a very important biological indicator, particularly for diagnosis as well as for treatment of diseases like diabetes. And insulin delivery is also important for the treatment of diabetes. Some quick and important background information. Diabetes refers to a chronic disorder in how the body processes food into energy. Most often it's type 1 and type 2, which can be categorized as type 1 referring to an inability to make insulin, whereas type 2 is insulin resistance. Insulin is a hormone that regulates uptake of glucose. And normal blood glucose values for frame of reference are 100 milligrams per deciliter. Fasting, say after you wake up in the morning, is around 70 milligrams per deciliter. And after eating a large meal, can go as high as 120 to 140. Above 140 is pre-diabetic, and above 200 is dangerous and diabetic. So in order to measure blood glucose levels and deliver insulin in a non-invasive manner, we plan on implementing near-infrared spectroscopy and the use of hollow microneedles to minimize risk of infection as well as pain for the patient day-to-day.
All right, so we're going to talk about some previous devices that are currently on the market and used for blood glucose detection that we referenced and to get ideas for our time. So this is a continuous glucose monitor. However, it uses an invasive metric where it requires a needle to be injected underneath the skin. The image on the right shows the wire that goes underneath the skin. It's a gold wire coated in an enzyme glucose oxidase, which when interacting with glucose, catalyzes the reaction to form glucose 1,5-lactone and hydrogen peroxide. The hydrogen peroxide then serves as an oxidator to the gold, and that oxidation yields a current in the gold proportional to the blood glucose, which can be received by a system and can be calculated into a blood glucose value. Second device that we referenced was a Medtronic insulin pump. So to get an idea of how current devices are used, the infusion set that goes into the skin has a small cannula that needs to be applied with an applicator that uses a small needle to inject the cannula under the skin. And it connects to the insulin pump, which has a reservoir where the insulin is stored, and then based on whatever values the doctor dictates for the blood glucose value, the insulin is injected for a certain volume by a piston, which injects that into the tubing and into the applicator. The third device that we referenced was a pulse oximeter. As we discussed, we wanted to try a non-invasive device of infrared, so we looked at a pulse oximeter that uses red light and infrared light to measure the blood oxygen levels based on the oxygenated and deoxygenated state of hemoglobin on red blood cells, and based on those calibration curves that are pre-established, this device can show you your blood oxygen level.
So part of our design process was interviewing a patient. So we interviewed a 22-year-old female who had type 1 diabetes since she was 9 years old, and we asked her just some basic questions. Our first one was about the current setup that she has that is invasive. We asked her how painful it was from a scale from 1 to 10, 10 being obviously the highest. And she said if the cannula inserts correctly, it can be about a 2, but if it doesn't, it can be up to a 7, which is pretty painful. And so we asked her if she'd change to an infrared system if she could accurately display the blood glucose levels, and she said yes, as long as it would be able to provide other data that her system does. And we also asked her if she would replace her current pump for the microneedle patch that we were proposing, and she said yes, as long as it's relatively reasonably affordable.
All right, so here's a list of specifications that we derived from prior literature and the interview, where we stated the device needed to measure blood glucose from a range of 0 to 300. These milligrams per deciliter, these numbers are from the standard biological data that the typical person needs to be able to measure with diabetes or healthy. We also said for the insulin pump, it needs to be able to deliver 0 to 35 units of insulin in either a bolus or basal manner, or bolus being an all-at-once delivery. Typically, patients do this right before a meal to cover the glucose broken down in the meal, or a basal, which is in smaller doses continually over time. The device also, we stated, needed to be less invasive than the current devices on the market as the scope of our project. The standards we wanted to abide by were the FDA guidance, which basically states what you need to do when you're designing a medical device and the whole process for research and design. The ISO 15197 talked about the accuracy standards that needed to be for a glucose meter at different concentrations. The ISO 11073 talked about how often the glucose monitor needed to detect values to be considered a continuous one. And then the ISO 10993 talked about the safety and biocompatibility the device needs to have with the body.
So this is my design concept. Essentially, it's a watch in which the infrared light and sensor are going through the bands of the watch, essentially, and so it would send and receive the signal through the wrist, and it would display the current blood glucose level on the face of the watch as soon as it's up image, and all alongside it would be a microneedle patch that would be placed and disposed of, kind of like a band-aid, essentially, with a cartridge attached to the back.
So this is my design concept. Firstly, we have the microneedles, which are being integrated in the form of an infusion set that can be made to be compatible with these existing devices to maximize the more patients who can use it. Next, we have the earpiece sensor. So the blood glucose monitor would go around the ear, sort of like a Bluetooth device. There would be a component on the top that would wrap around your ear, and the LED and diode would line up magnetically and be able to measure blood glucose from your ear. The reason why I chose the ear was because the tissue is much thinner here, making it easier for the light to pass through, and there's enough vascularization to accurately measure the blood glucose values.
All right, here's my design. I also did a wireless microneedle patch that would deliver the insulin from a reservoir contained in the patch. And similar to the insulin pumps, I used a piston mechanism that would deliver a set volume for whatever blood glucose value was obtained for the patient who needed it. The the infrared sensor I incorporated into a watch as well, where the LED was in the back of the face and the photodiode was on the opposite side in the clasp, and they would all connect with an electric system that was in the watch face to to calibrate the signal and show the blood glucose value on the surface and face of the watch. So here's our decision matrix. As stated in the previous presentation, we scored everything out of 10 and then weighted it to get a percentage. We evaluated them based on sensing the glucose in the optimal location, delivering the insulin effectively in that location, user interface friendliness, satisfying the design standards, and being less invasive than current models. And we chose not necessarily the best option, but the best components of each option to create our final design, which is shown here. We have a microneedle patch that would be part of an infusion set that just connects to current insulin devices. The infrared sensor was incorporated into a ring. We moved this from the watch into the ring as it was a more concise thing, and we can move the light and diode off to the side to try to avoid the bone as much as possible. We used a 1550 nanometer light because we saw that was the maximum wavelength that would be absorbed by glucose and avoid other solution and media. And the whole system would work by sending a signal to light the light. The light would propagate through the tissue, be picked up by the diode, processed through a filter and amplifier, and then sent to a microcontroller that can then distribute the signal to any paired device for the user to read and use and interface with.
So this is our final design for the microneedle patch, essentially. So this is meant to work with the Medtronic insulin pump, essentially. So it would be pressed fit into the inlet, the tubing, and the insulin will flow through and go down into our 10x10 microneedle patch array. And here's a cross-sectional picture as well, just so you can get a better idea of what the inside of the chamber looks like. As you can see, this is where the tubing would be pressed fit in there, and then the insulin would come down and through to the microneedles.
Here we have the design of the individual microneedles. Here we have a 3D model to pass around so you can view. It's a 50:1 scale. This 3D model is 50 millimeters tall. Our actual design is 1 millimeter tall. That length was chosen in order to maximize delivery depth while minimizing the amount of pain for the patient. And our research showed that 1 millimeter was the sort of threshold before pain started to increase significantly. The material we chose for the microneedles was silicon. This was due to its high Young's modulus, its non-ductile nature, and then its injection hardness or implementation hardness, which made it an optimal material candidate for microneedle fabrication. The shape of the microneedles was chosen to maximize structural integrity, and the location of the opening was also offset from the center to make application better by keeping the pointed tip intact. It's to also help reduce clogging upon application, and then it also helps in ensuring the structural integrity of the device.
All right, so here's the design that we made for the ring. The left two images show the fusion model. The holes that you can see there are for the photodiode and the LED to be incident on the skin. The right model you can see is a 3D printed version that we have here. We can pass around. The two components have threading on the inside and outside so they can be put together, and the holes as well are incorporated into that for the LED. It is on the smaller scale than what would be needed for an adult finger, but we just created sizes as it would constantly change based on the person's finger size. So here are some cross-section views to help get an idea of how we would lay out the ring. The left image shows the threading on the top and bottom as they would screw together for the components. The middle image, you can see that black portion, that's a rubber gasket we designed to try to minimize any exposure to any fluid that could potentially compromise the system. And then the right image shows a potential schematic where we would have the LED and photodiode facing each other, offset from the center, and then the electronic components laid around the inner portion of the ring, all connected in a system that would allow the signal to be filtered, amplified, and then processed for blood glucose calculation. So here are just the three components separated. The left image is the inner ring where the electronics would be incorporated. The middle image is the rubber gasket, and then that right image is just the outer shell that closes everything together.
So whenever we're going to go through our adherence to our standards that we set out, first we have FDA 0957, which refers to the design of a medical device. We adhere to these standards through many different means, namely being meeting as a group to discuss all potential changes, as well as keeping a detailed account of all the changes we made and reasoning as to why we made those changes. Next, we have ISO 5197, which relates to the accuracy of our device. This standard determines that for blood glucose concentrations under 100 milligrams per deciliter, you need to be within plus minus 15 milligrams per deciliter. And for concentrations above 100 milligrams per deciliter, you need to be within 20%. The table below shows blood glucose samples prepared in rabbit blood at different concentrations, and it shows that we fit well within the standards set out. Next, we have ISO 11073, which refers to continuous blood glucose measurements. And the hardware that we chose for our design is capable of sampling at 1000 hertz, meaning that it falls well within the 5 minutes required. Now we have ISO 10993, and the two major biomaterials being used are silicon and titanium, as those are the two things interacting with the patient. And both of those materials satisfy 10993 for their proposed use.
So this is the test box that we successfully made, and it was designed around a standard 3-inch test tube. And unfortunately, due to the curvature of the tubing, we had issues with the photodiode and ultimately light refracting, and it wasn't getting there, and so our values were skewing. So we ended up changing our design to the second box, which is this one, which you can see the diagram on to your right. And so that diagram shows essentially that the LED light will go through the platform essentially with a hole cut out that is roughly at the size of a well plate that we configured for. And the light passing through will reach the photodiode, and that photodiode will translate it to a prototyping board and ultimately to our lab view, which then can be processed to get data.
Alright, so here's the lab view front diagram and block diagram that we use to analyze the signal. So we acquired the voltage from the setup, and that was filtered through the continuous data acquisition, and then put through a low-pass filter with the 1.69 frequency, and then amplified by 2, just so we got a visible signal to analyze with. And then, based on the concentration curve that you'll see on the next slide, we plugged in the equation that we got, and then we're able to use that to show the blood glucose value based on the voltage.
And the diagram here shows the readout for 125 milligram per deciliter blood glucose concentration.
So here are the two calibration curves. We tested both glucose in water solutions and blood solutions. The water solution we tested at 2 different heights, as bringing the photodiode a little closer to the LED created a slightly stronger signal. So that's what we used to explain the difference in the 2 waveforms in the graph. And we tested these in from 0 to 300 milligrams per deciliter and 50 milligram per deciliter intervals. The chart on the right shows the concentration of glucose in blood. That was tested with both cat blood and rabbit blood. The difference between those 2 curves, well, it appears small on there, is due to the cat blood being provided as a solid, so we needed to add water to rehydrate it, which caused the solution to be slightly diluted, so it affected the signal being obtained. The water had a positive trend while the blood had a negative trend, and we attribute this with the water interfering with the LED signal, so it amplified the signal as it was picked up by the photodiode. However, with the blood, it reacted as expected, where the more glucose that was there absorbed more of the LED light, so it reduced the voltage obtained by the photodiode. So here we tested the stress of the titanium ring. So we analyzed it in console. On the left image, you could see arrows pointing. This was a 1-point stress test, as if you were wearing it and you just pushed on the ring or you banged it against something. We tested a 200-pound force, and the titanium has a 240 megapascal yield. So the middle graph shows the von Misses, and the right graph shows the factor of safety, where the factor of safety is the ratio between the yield stress and the von Misses, and therefore any value that would be less than 2 would technically fail and go past the yield point. And based on the color showing, most of it is above the fail point, and it is mostly 2, so it would pass the factor of safety. These images are for the same test, but the deformation scale factor was amplified to 100 to see what it would come out to if the stress was amplified that much, but the factor of safety and von Misses did not change. We then tested this again if we put 2 points, so if you were gripping the ring from both sides, pulling it on and off your finger. We calculated this again with the von Misses and the factor of safety, and then you can see on that right side with the same load applied and the yield that the ring is fully in the blue and above the factor of safety. And then we increased the deformation scale factor to 250 to see how it would deform, and based on that load applied, it would have that curvature in nature along the band.
So we also tested the microneedle patches rolling console using turbulent flow. And we actually scaled down our model to the computational limitations, and so we only did a 3x3 array. And as you can see, the streamline velocity to your left, and you see that the velocity increases as the diameter decreases, which makes sense. And it is you can see that all of the velocities and the pressure is all well within the capability of the material we chose, silicon. So we modeled our dynamic viscosity and density of the insulin based using fast-acting insulin, which is compatible with the Medtronic insulin pump, which we picked out. And we got an outlet flow velocity of 6.18 millimeters per second.
So now we have our safety and risk analysis. We've identified 5 potential points of failure on the device. First and foremost is the individual microneedle integrity upon application. This is the most likely point of failure. However, Due to the measures we've taken, we believe that it's unlikely that a majority of them would break, or even that many of them would break. So there's likelihood that at least one of them will break, but the severity of this occurring is not a major problem. Next, we have the microneedle plate integrity during everyday use. This is what the microneedles are directly attached to. This device is being used for everyday usage and is therefore can be influenced by a variety of different factors and could potentially break. However, we do believe that this is not extremely likely to happen. So while if this were to happen, it would be a severe problem, but we do not believe that it would happen very often. Next, we have photodiode and LED water damage. As we said, we've introduced a gasket to try to minimize this, but this is being used as an everyday thing, so anything's possible. So if either of those were to fail, the system as a whole would fail, but again, we don't believe it's likely to happen. And then lastly, we have the ring integrity, which, again, everyday usage, you don't know, you never know, somebody could run the ring over with a car. Again, as we showed with our console simulations, the ring is likely to remain intact during everyday use. Next, we have the bioethical analysis. There aren't very many bioethical concerns with that device, as it's not doing anything new. Rather, it's doing something that's already been able to be done in a much better manner. I.e., people, like blood glucose monitors and insulin pumps exist, but ours is much less invasive. Next, we have the cost analysis. The titanium ring housing is estimated to cost $600 per unit. The electronics of a comparable device with a $5.3 million investment were estimated to cost $2.3 per unit. And the silicon microneedle array was estimated to cost $370 per unit.
Here's our actual project timeline. And
Here are some limitations and constraints. So the ring is supposed to be used for the general public and interacts with the skin, and people can have dry skin, more moist skin, so on and so forth. This leads to an inconsistent medium, which presents a potential problem with the accuracy of the device, person to person. Another potential issue is the glucose range. Values were measured between 0 and 300. However, we don't know if it can accurately measure values beyond that. And also the sensitivity, as our device falls well within the standard, but we're not accurate to the nearest digit in particular. And then we have IR penetration through the skin. The tests that we performed were done with just blood, the well plate, which does not reflect how it would actually be used day to day. And if this was to be used through skin, it would likely need much stronger IR lights than we used for our experiments. And then the stronger lights would end up using much more power, which presents a potential issue with the device's battery life.
These are some of the lessons learned. This is just an amalgamation of all the stuff that we learned along building all of these things. Essentially, just doing the research and development process and like using console execution throughout our modeling and the making of the microconstruction. And this is just a couple of acknowledgements. We'd first like to acknowledge Professor Smith for obviously helping and giving us guidance and support throughout our project. But we'd also like to thank Rob and Mr. McKenzie as well for helping with the prototyping of the box and for the 3D printing of the ring and the microneedle. And we'd also like to thank Professor Gloria for helping us with the lab, lending us the lab to prototype forward.